Okay, so looking at the cube root of 2 to the 4th. We have looked at roots as powers before. The example that we've considered was like x, or in particular, the square root of x. What was my exponential way of rewriting the square root of x? X to the 1/2. And so what is the analog going to be for the cube root of x? X to the 1/3. And if I was taking the 5th root of x, it would be x to the 1/5. And if it's the 10th root of x, x to the 1/10, so on, x to the 1 over 100, the 100th root of x. Roots are just fractionalized ones. It's going to be 1 over the size of the root that we are taking. And so rewriting this expression here, this is going to be 2 to the 4th, all raised to the 1/3. And then exponent rules. If I have an exponent raised to a power, what can I do with those two powers? Multiply them together, I get 2 to the 4/3. And so log base 2 of 2 to the 4/3 is just going to be equal to 4/3, absolutely. All right, let's take a stab at B here. We have log base 2 of 1. How can I rewrite 1 as a power of 2? 2 to the what? 2 to the 0. Very good. So this is log base 2 of 2 to the power of 0. And so what is my exponent here? Just 0. Very nice. In fact, any log base anything of 1 is just always going to be 0, because any base raised to the power of 0 is just going to be 1. Very, very good. And then lastly, for C, we're given log base 2 of negative 32. Now 32 is just 2 to the 5th, so that one wouldn't be too bad if it was positive 32. But in this case, I'm asking you to take a positive base, raise it to a power, and get a negative output. Is that possible? Can I take a positive base, raised to a power, and get a negative? No. And so is there any solution for log base 2 of negative 32? No, this is just either D&E or no solution or what have you. I'm not actually exactly sure what the super proper verbiage is here. I'm going to go ahead and say no solution. This ties in very, very handily to the domain of our logarithm. Yesterday, when we were kind of building up this inverse function, what did I say must be the domain of my log? Domain of my inverse was 0 to infinity. So the output, the exponents themselves, can be anything, but the result is only ever going to be positive. So I can only plug positive numbers into my logarithms for them to spit out and tell me some kind of exponent. Right, if I plug a negative in, it just doesn't make sense. I can't take a positive base, raise it to a power, and get a negative unless we're using imaginary exponents or complex exponents, which for now we are not. And in fact, we might not ever. We might look at it at the very end. It'll make a lot more sense if we actually do look at it. Yes.
So how did we get like the yesterday when we did the one where it equals -8?
Yeah.
So, what is it that we can't have negative?
So you can't have negative inputs, but you can have negative outputs. And in particular, negative outputs are when we do what to our base? Take the reciprocal. So if you ever see a reciprocal of your base, so for instance, notice here, we had a base of 1/5. And when we take that reciprocal, we're suddenly working with a base of 5. So that's how we knew that this was going to be negative. because we're doing reciprocal. So our outputs, our exponents can be negative, but our inputs, that result, is never going to be able to be negative because base raised to a power when the base is positive can't be.
So with the input in this one that doesn't work, be like, would that be negative 32?
Yeah, so because the negative 32 is an input, we're plugging it into our logarithm, we won't get an output. There is a thing that we will get matched to. Okay. Good question. Any other questions? Okay, as far as, say, like a quiz or a test, where if I were to ask you to simplify a logarithm without a calculator, okay, probably something that you would be more likely to see on a quiz, since I can be a little bit more choosy with on a quiz, the types of questions that you'd be asked to handle. But if I ask you to simplify using the identity operation, right? Would I have considered these questions fair game before the button? Probably not. These are a step above what we were working with yesterday. This was supposed to be a difficult build. This was not supposed to be super straightforward. No sort of overtime. Would I consider these fair game on a quiz that we have after the spell work? 100% yes. These are absolutely techniques that I kind of expect us to be a little bit familiar with, right? So this idea that a cube root is the same as the power of 1/3. The idea that taking a reciprocal is the same as the power of -1. The idea that log base anything of 1 is 0. Right? Those are, and even if I try to plug in a negative, that I won't get a result. Those are, I would say, kind of the upper echelon of questions that I could reasonably ask, but I do consider them to be questions that I could reasonably answer. Right. So difficult bell work, but hopefully once you see it, once you've kind of seen it once, it makes a little bit more sense. At the very least, it's kind of like where to start. Very much kind of in line with, say, what you might be expected to do on like a quiz that you might hypothetically have on, say, like a Tuesday of next week or something. You know, just hypothetical. All right. So today, well, a couple of things. First of all, today is, we're going to do like kind of a proof day today. We got some properties that we're going to look at. We're going to look at where these properties come from, and then we're going to mess around with these properties a little bit, see how they work. All of these, I will say, I'm not always going to show the connection that these have with the corresponding exponential properties, but do kind of note in the back of your mind that our properties for logarithms come from the fact that we are working with exponentials kind of at their core. And in particular, something that I want us to kind of have hammered into our brain for forever, the output of our logarithms represent what? They are exponents. So every single kind of thing here that we are going to see with our properties is some kind of operation with our exponent based on something that we're going to be plugging into. All right, so we're going to be altering what we plug into our logarithm, and we're going to say that's going to have some kind of effect on what we do with the exponents, and what you get as a result with the exponents. We are going to start with the product rule for logarithms, which says that if I have log base b of two numbers multiplied together, we're going to say m times n, then this is the same as log base b of m plus log base b of m. Okay. So before we jump into the why this is true, which we are going to jump into, but before we do that, I really do just want to kind of convince ourselves that this is in fact true, right? So what is this really saying here? Well, log base b of m times n, this is a logarithm, so this is like our new exponent that we get when I multiply two numbers together. When I multiply two numbers together, assuming they have the same base, assuming that we are in base b, how do I combine the exponents? For instance, if I have like 2 to the 4th times 2 to the 5th, what do I normally do with the exponents? I add them, and so we're saying that our new exponent that I get when I multiply my results is the same as taking the sum of my two smaller exponents. So hopefully very, very consistent with kind of what we have seen with exponentials up until this point. But we're going to kind of codify that. We're going to put that into a little bit more precise detail here with just a quick little proof. I'll kind of go through it. So our claim, the thing that we are trying to show, and this isn't something that you guys have done a little bit of proof work in geometry, I know. Normal proofs don't normally have that kind of like block format of like the theorem and then the thing that you're using. And just kind of a nice little thing. We might look at this at the very end of this class, we'll see. I just kind of like to tell the reader what I am actually trying to show, just so that you know that I'm not claiming, like I'm not saying right now that this is true, I'm just giving you like an indicator, hey, I'm trying to show this. This is the property that I'm trying to show. In particular, I'm trying to show that log base b of m times n is the same as log base b of m plus log base b of m. All right, now we're going to be talking about these kind of exponents here. It might be helpful to just be able to define these as exponents. So we're actually going to start this proof by just kind of sectioning off. We're going to use a little bit of a dummy variable. I'm just going to kind of add as a placeholder for now, just to make some of the notation a little bit easier. We're going to just set x equal to one of these powers, y equal to another one. X and y here, they're really just placeholders. They're just to kind of allow us to talk about what we're working with here. So we're going to let log base b of m be equal to x, and log base b of n be equal to y. Again, that just lets us talk about these as if they are exponents. Okay, here's the practice bit for you. I'm going to be doing most of this, but just a little bit of an opportunity to reinforce what we did yesterday. I have here a logarithmic statement, and for some reason, which we'll see here in a moment, I want this to be an exponential statement. How can I rewrite these two logarithms as exponential statements? What is the same thing as saying that log base b of m is equal to x?
B to the power of x is equal to m.
Very good. That b to the power of x is equal to m.
And power of y is equal to m.
And that b to the power of y is equal to m. Very good. Now, what are we actually concerning ourselves with? Well, we don't really care about m and n on their own. What do we actually care about? Well, we care about the log, but then we also care about what happens when we multiply them together and then take the log. So let's try multiplying m and n together and see what we actually get here. So m times n is going to be equal to. So what's another way that I could write m times n here? That might be useful. So this is going to be, say, b to the power of x times b to the power of y. Okay, and here's the bit where we actually see the transition from multiplication to addition. What do I do with my exponents when I take base to an exponent times base to an exponent? We add them. This is going to be b to the power of x plus y. Okay, But just like Nikaya said, we're looking not just at this product, but we are wanting to take the logarithm of this product. And so log base b of m times n, well, really that's just the same as what? Log base b of b to the x plus y. And what is log base b of b to the x plus y going to be? That's just x plus y. Right. But x plus y are just, those are just placeholders, right? What is x really? Yeah, that's just log base b of m. Plus, what is y? Log base b of m. And that's what we're showing. That's what we're trying to show. Right? That, when I take the product and take the logarithm, that I end up getting the sum of the original two exponents. Which again comes from this kind of exponential property right here, where when I do b to the x times b to the y, how I add the exponents. But I condense into a single piece. Okay, so what does this give us the power to do? Why are we going to use this? Well, it gives us a couple of things, but what we're going to be doing today is this allows us to split apart a really large logarithm into a bunch of smaller logarithms. It would also allow us to take a bunch of smaller logarithms and combine them into one larger logarithm. We'll do that tomorrow. But for now, we're taking big logarithm, splitting it apart into a bunch of smaller logarithms. Something that I want to note. This is something that you guys need to be very, very careful of. The number one mistake that I see, just like every single time when I'm teaching this, the number one thing that people mess up. This is the product rule, right? This only works if we have on the inside of our logarithm a product. If I have log base b of a plus b, or a plus c, or whatever, it doesn't matter. I cannot split this apart. I can't split apart across addition. I would either need to figure out some way to rewrite this as a product, or I'm just toast. There's just nothing. All right, so we want to be very, 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 very careful that what we are looking at is not a sum, but that it is in fact a product. And we'll see a couple examples where we are given sums and we can rewrite them as products. But then we'll also see some examples where we're given sums and there's nothing that we can do to rewrite them as a product. And that just is what it is. This is just what we end up with. And so sometimes you end up with some pretty nasty looking logarithms that like can almost be split apart, but really we just can't do anything about it. So let's take a look here at our example 1. We're going to do this pretty by the book for the first one. We're going to be very, very precise here with how we use the product rule. In particular, notice that the product rule says if we write the inside as a product of two numbers, that we can split each one apart into m and then n. So we're going to be very precise with that, and then afterwards we are going to be able to shortcut it just because we're going to make the observation of, okay, well, if I have a product of 3 numbers, then I can split it apart into 3 numbers being added together. If I have a product of 4 numbers, then I can split it apart into 4 numbers, and that's fine. But at least for this very first one, I want to be very precise with how we are using this product rule. So looking at log base 3 of x times y times z. First of all, is this a product that we're looking at? Yeah, okay, so we don't need to worry about any addition or subtraction nonsense going on. These are all being multiplied together. That's good. What would be a good value for m, and what would be a good value for n if I'm trying to kind of split this apart? Perfect. So we could let m be x, and we could let n be yz, and there are what, like 2 other combinations that we could have done that would have been just as good, but this one works great. So however you want to divvy this up is totally fine, but I like going with this idea of saying that this is log base 3 of x times yz. Where now x is our value of m and yz is our value of n. What can we then do with our product rule? Split this up. This is going to be log base 3 of x plus log base 3 of yz. Okay, so now looking at this, is it as split up as it possibly could be? No, what else could I split apart? I could split apart by yz. Notice this is y times z. This is like a new m and a new n. And yeah, absolutely, we could now write this, and in fact, you should now write this as log base 3 of x. That's perfectly happy. We're happy with that. And now we're going to split apart the yz here into log base 3 of y and log base 3 of z. Okay, so technically speaking, our product rule says we can only do it with two numbers, but then we could just do the product rule over and over and over and over again until we end up having it fully split apart. So yeah, you could just jump to the end here, and that would also be totally fine. You don't have to break it apart into numbers. I just wanted to show you technically by what the product rule says. This is the most precise way to do it, but yeah, from here on out, you're able to just split it into the product of all these numbers. That's fine. All right. That was example 1A. Hopefully pretty, not too bad. Okay, cool. Let's look at one that's a little worse. B is whatever. I'll have you guys work on B here. I want to take a look at C here. C is a little bit tricky. What do I notice about C that's going to be a problem for when I'm trying to use my product rule? Okay, we have addition here, right? So we've got this kind of plus going on. So as it stands right now, is what I am looking at a product? No, it's currently a sum, not a. All right. So I need to be able to rewrite this as a product, or maybe it's impossible to rewrite as a product, and we just go, oh, I'm going to call it a day. But this one actually is going to be possible to write as a product. What could I do to write this sum as a product? Yeah, factor out the 30. And so we could rewrite what we see here as log base 4 of 30 times x, y, z plus b. Right, dividing 30 out from 30xyz, we use behind xyz, dividing 30 out from the b, leaves behind b, kind of doing distribution, but in the other direction. All right, fantastic. And so now what is our value of m going to be? 30, and now what is our value of n going to be? X, y, z plus b. It's a little messy, but that's okay. We aren't actually even going to need to do anything with this. Is this ever going to be able to be written as a product? No, it's just going to be kind of ugly, no offense to it, and it's just going to chill where it ends up. Right? So we're gonna be pretty happy with that. So this is going to become log base 4 of 30 plus log base 4 of x, y, z plus b, where, like we just said, we can't really do anything here because this is always just going to be a sum. It's not going to be a problem. Now, what can we do something about? So we can't do anything about x, y, z plus b, but there is still a product here that's going on that I can split up further. 30 is numbers multiplied together. In particular, how could I split up 30? What is 30 going to look like? 3 times 2 times 5. You could do like 6 and 5, but then we could split up the 6 into a 3 and a 2. However you want to do it, you can write it as a product of, in this case, we're looking at primes, so 3 times 2 times 5. Right. Or you could do like 10 times 3, and then the 10 splits apart into a 5 and a 2. Any order you do it in is totally fine. And so what does this end up being? Well, if we're looking at 5, 3, and 2, is going to be log base 4 of 5 plus log base 4 of 3 plus log base 4 of 2. I'm going to actually go down here, plus log base 4 of this thing that we actually can't really do anything about, this x, y, z plus b. Don't forget that he's there. He's just not able to do anything about it. And so this would be our kind of fully expanded logarithm. One quick thing to note, which is again kind of the benefit, perhaps benefit, of why we are doing this, what we are doing here. Log base 4 of 5. Is there an easy, nice, clean power that I can raise 4 to that's going to make it equal 5? No, that's going to be a bit of a mess. Log base 4 of 3, is there an easy, nice, clean power that I can raise this to that's going to, no, that's going to be a bit of a mess. What about log base 4 of 2? 1/2 is going to be the log base 4 of 2. And so you could leave things like this. I would take this, and this is perfect, and this is great, and this looks beautiful. You could also replace the log base 4 of 2 here with a 1/2. And I'm mostly noting this just to say this is probably what Pearson would want you to do. Just fully simplify this, noting that this does just become 1. What power do I have to raise 4 to equal 2? Well, we have to take the square root. Taking the square root of 4 is the same as raising 4. Yeah, so.
Would we not write the log either? You just take this one.
Yeah, this whole thing could just be replaced with 1. But also the way we have it written here, I'm perfectly happy with. That would also be totally fine. Questions with C? All right. Let's take, we'll say 5, 10 minutes. Take a stab at B and D. So notice B is what we were looking at here, a sum or a product. Product, we're already ready to do product rule, that won't be too bad. And then D, what we're looking at is a sum, so how can we rewrite it as a product? Factoring is going to be our friend there. Is there anything that we can kind of bring out to the front there so that we can split it apart with the product? Yeah, where did it become? Yeah, perfect. It would just be, yeah, just like, yeah, what power do we have to raise 5 to equal 5? It's just good eye.
Trying to understand a little bit more.
Okay.
Kind of like factorization.
Kind of, yeah, you're breaking apart each of the products into each of the factors, pretty much. So if it's a lot to kind of jump straight from the 30 into like the 5, the 3, and the 2, then break it into like medium-sized pieces, and then break the medium-sized pieces into smaller pieces. So like break the 30 into a 3 and a 10, and then break the 10 down into the 5 and 2. Just make it a little bit easier so you're not trying to skip all of this. Super good. And other one, this one. Start 2. One thing real quick. Can we split the 6 part? Yeah, perfect. Very nice. And you could have written it as log base over 5 as well, and that would have been correct as well, but 1 is the super precise way to do it. Yes.
That's right here.
Yeah, rather than breaking it up, I like that. I like that idea. Okay, so let's start. Let's just break this into like manageable chunks rather than kind of trying to do it all at once. What would be a nice like value for m here, a nice value for n here that would allow us to just like separate this and make it a little easier? So we could do 5 and then 6, but we want to include the xyz as well. So I kind of like the idea of doing like 30 and then xyz, so that we like separate the coefficient and the variable. But you also could do like 5 and then 6xyz, and that would be fine. Or you could do 5 and 6 and xyz, and that would be fine as well. Ultimately, what's going to happen with the xyz? What are they all just going to do? I mean, pretty much exactly. Yeah, they're all just going to break up, kind of like what we see here as well. And then the 30 is going to break up very similarly to how we saw here. Okay, so we can pull out a 2, and that would make it 5. Is there anything bigger that we can factor out to the front? I think 6 is going to be a really good one, because 6 divides evenly into 12 and 30. So try factoring out 6, and then that 6 is going to be your n, and then this garbage is just going to be your n. We're not really going to be able to do much about it, because that plus is going to make things really kind of similar to how this xyz equals b just kind of stay there. Not able to do much about it. How are you? This looks good. And then could we break apart these even further? So this one, 30 is going to be the same as, yeah, that whole thing. And then XYZ is like the, like what was out there? Yeah, exactly. So it's going to be just like both of those, but added together basically. With the different things. Yes. That's good. No, you're good. Yeah, that's perfect. Yeah. Both of those I would accept as being as simplified as we can. Okay. Either way. Yeah, and I'm fine with either way. You can either fully. Now, this is good. Can I break apart my 5xy equals 2? That plus 2 is going to give us this. Oh, can't break apart over addition. And so it would just stay as 5xy equals 2. Just leave it as that. So you could think of it as like x times x times x. But we're going to look at here in just a second the power rule, which allows us to do with it. But thinking of it as x times x times x is not a bad idea at all. We'll just be looking at it. We'll have a rule that lets us like just consider it. Yep, that's just one. All right, let's take a look here at B. So this is already just a product. If we wanted to break this apart into pieces to make it a little bit smaller, we certainly could do that. What would be like a good value of m and a good value of n to just like separate this into 2 more digestible chunks? Yeah, I like separating the 30 and the xyz if you are struggling to separate it all at once. So writing this as, well, this is going to be log base 5 of 30 plus, actually I'll go down here. This is log base 5 of 30 plus log base 5 of xyz. We've already looked at this, but how is the log base 5 of 30? How is 30 going to split up? 5, 3, and 2. So this is equal to log base 5 of 5 plus log base 5 of 3 plus log base 5 of 2. And then how is my xyz going to split up? Pretty much exactly like what we saw from example 1, right? So this will be like log base 5 of x plus log base 5 of y plus log base 5 of z. So a little bit long, but ultimately it's basically just like the 30 bit from the example C added with the xyz bit from example 1. With a different logarithmic base here, of course. So if the 30 xyz all at once is being overwhelming, break it apart, deal with the 30 first, deal with the xyz second, and then you're just adding them all together at the very end. Much better. All right, now for D, is this a product? So can I just jump straight into the product rule? No, this is a sum. And so what was kind of the factoring that I could do to rewrite the product? Yeah, bring out a 6. So this is log what's going on here? Internet has crashed. That's good. That's ideal. All right, 1 second. Cool. All right, so splitting this apart into 6 times 5xyz plus 2, m in this case is 6, n is 5xyz plus 2. Am I going to be able to really do anything with the 5xyz plus 2? Not really. That's a sum. It's not going to split apart at all. I get log base 6 of 6 plus log base 6 of 5xyz plus 2. And then just kind of a quick thing to note here, log base 6 of 6, I could either split 6 up into what? So this either is going to be log base 6 of 2 plus log base 6 of 3, or what else could it be? Or this could be 1, kind of similarly to how log base 5 of 5 could also be 1 as well, but either of those would be counted as fully simplified. Both of those are perfect. Zoom in to here. Yeah. So questions here with example 1. All right. Okay, 2 more properties to talk about. Normally when this is presented, you probably get product rule first and then quotient rule and then power rule. I switched the order here, mostly because quotient rule is what you get when you do product rule and power rule at the same time. So let's learn about power rule first so that we can apply it so that quotient rule is really nice. All right. So what is the power rule for our logarithms? This says if I have log base b of x to some kind of power, we're going to call it x to the m, then I can rewrite this as m times the log base b of x. We'll talk about the logic. I know we did kind of like a logic rundown of why this one makes a lot of sense kind of beforehand. We'll talk about the logic on this one afterwards, just so you can kind of see the mechanism, see how this actually works, what this actually is. So we are claiming here that log base b of x to the m is equal to m times log base b of x. Or remind me again, what is log base b of x? What is this? It is an output to my logarithm is an exponent. Okay, so this is like saying that I can find the new exponent by multiplying the original exponent by m. Okay, interesting. And so how are we going to go about and show this? It's actually a pretty straightforward, I say with a little bit of an asterisk, but a pretty straightforward application of our product rule. So let's suppose that we have, well, consider log base b of x to the power of m. What is x to the power of m? What does that kind of mean? Just thinking back to like our super basic understanding of exponents. If I have x to the power of m, what is that telling me to do? Exactly. So this is basically saying that I have log base b of x times x times x times x dot dot dot. And how many times am I doing this? M times. Okay. Which means I have the inside of my logarithm is what? It's a product. And so what can I do here if the inside of my logarithm is a product? Product rule. We're going to break it apart. We're going to add them all together. When I break it apart, what do each of my pieces look like? Yeah, exactly. This is log base b of x plus log base b of x plus, and how many of these log base b of x's am I going to have? I have m of these. So I'm adding the same thing to itself over and over and over and over again. What's another way that we represent repeated addition? We do it with multiplication. So this is just the exact same thing as m times log base b of x. Right. So not a too horrible one, just kind of basically product rule over and over and over again. Kind of. Honestly, this proof leaves a little bit to be desired, but that is something that I will ask you to think about when we do a challenge set for this. I will post this. Okay, but again, kind of the intuition of what we are looking at here. If I am squaring my result, what am I doing to my exponent? So for instance, if my result is 3 to the power of 4, and I square it, what am I doing to this exponent here? I'm multiplying it by 2. So this is actually also, yes, we can apply the product rule to get it, but also this is just another exponent rule, kind of in reverse here. So what are we doing? Well, we are multiplying the exponent of our original result by whatever power we're raising it to, which hopefully should make a lot of sense if we recognize this power rule here of when I take a base raised to a power, kind of exactly like what we saw in example 1 here, 2 to the 4th to the 1/3 is 2 to the 4th. Right? We multiply those powers together in the same way. That is exactly what this is asking us to do. M times log base b of x. M is our new power, log base b of x is our old power. We are multiplying them together. All right. Okay, so that is our product rule. Moving along then, just really quick kind of pit stop at the very end. Technically, product and power rule could get us really, really far, like as far as we want. We'll combine the two into our quotient rule. So this is log base b of two results that are being divided together. If I take a result and divide it by another result, what do I do with the exponents? We subtract the exponents. This is going to be log base b of m minus log base b of m. All right. Okay, this is a very, very, very straightforward application of both the product rule and power rule. So how are we going to do this? Again, we'll just go through this one. This one's pretty quick as well. This is log base b of m over n, and our claim is that, well, this is really, we are subtracting these two powers here. Our new power is the difference in our original powers. So let's again consider think how you would feel if this were you. All right. So we are again going to consider log base b of m over n, but I'm going to rewrite this as a product. So this is something that you can always do when you are dividing numbers. You can always rewrite them as multiplication. For instance, if I'm dividing 3 by 2, I can rewrite it as 3 times what? So 3 divided by 2 is the same as 3 times what? 1/2. We could multiply by the reciprocal. So I'm actually going to rewrite m divided by n here as a product so that we can use our product rule. So this is going to be the same thing as log base b, so that implies this is equal to log base b of m times 1 over n. Okay. I have the product of two numbers. What can I do? I can split them apart with addition. So this is going to be the same thing as log base b of m plus log base b of 1 over n. This is by the product rule. Okay. So now the only thing we really have to clean up here is this 1 over n situation. How can I rewrite 1 over n to become n raised to some kind of power. How do I create 1 over n with an exponent? N raised to the negative 1. Very good. So this is the same as log base b of m still, plus log base b of n to the negative 1. And now our new power rule lets us do what with that negative 1? We can move it to the front. So this is log base b of m minus log base b of n by the power rule. This is actually why the exponent rule that we use works. If I do b to the power of x divided by b to the power of y, you guys probably know this as b to the x minus y, and that's certainly true, but this is also just the same as b to the x times b to the negative y. And when you add the powers, you also get b to the x minus y. So really, this is a very robust proof because it also is why the exponent rule works the way the exponent rule works.
What's that little 0 below the n? That little.
That's a box.
Oh.
So whenever you are doing a proof and you want your reader to know that you are finished with the proof, you do some kind of notation to let them know, hey, by the way, we're done here. We proved the thing that we set out to prove. And oftentimes you will see this written in textbooks. It's like a little box.
I was just making sure you
No, it does not. That is my, you'll notice I put it at the end of, it's more obviously a box that by the way.
Yeah.
Yeah. That's just my saying, hey, I did the thing that I said that I was going to do. I finished my thing. All right. So those are all of our tools. Now we just need to apply them. So taking a look, we're just going to do one of these 3 from example 2. We'll look at the other 2 tomorrow. Taking a look at example 2, I gave my classes the choice here of which one they wanted to do. I'll give you guys the choice as well. A is fairly straightforward, so I figure we'll save A for tomorrow. Let's take a look at either B or C. What would you guys rather do today? Would you rather take a stab at B, or would you rather take a stab at C? I think I'm predominantly hearing C here. Okay, quick thing to note, I messed up my coding. I actually need to go back and change those spots on my mind. This is supposed to be base 11 in LaTeX. If you're not careful, it only registers from that first symbol here. So this is supposed to be log base 11, which makes it make a lot more sense because log base 1 is not a thing that we would want to even really consider. 1 to any power is just going to be 1, so it would not be a particularly interesting line. Okay, couple of different ways, all equally valid, but a couple of really interesting, good ways that we can approach C. Does anyone have any ideas with where they would normally work? What would you guys do if you were starting on C? If you were looking at this really, really complex logarithm, what would you do here, Adam? First step.
So I would take the square root and then just multiply the x, y squared and z by, or not multiply, but to take them to the 1/2 power.
Yeah, absolutely. That's totally something that we can do. So the suggestion here is that we clean up the square root. Ultimately, we're asking something about powers. And so let's rewrite the square root as a to the 1/2. I think that that's perfect. So this is the same as log, actually, I'm just going to focus on kind of the contents here, and we'll worry about the logarithm afterwards. So this is x squared y cubed, and then in parentheses, x, y squared, z, all to the power of 1/2. Now, when we have addition, we are not allowed to distribute this 1/2 like this, right? When it's addition, we can't do it. When it's multiplication, though, we can distribute the power, right? So if this was x plus y squared plus z, this 1/2 would not distribute. But because they're all being multiplied, the 1/2 can distribute, right? So this is not me telling you to distribute exponents and be happy. My number one thing that I want you to leave this classroom having learned is that you cannot distribute exponents if it were like this. that would just be that, that's it, we can't do anything with it. But because this is multiplication, whole different ballgame, we are allowed to distribute the exponents. Seriously though, there's one thing that you can learn that will make your future math teachers or math professors or whatever just so insanely happy. Learn not to distribute an exponent through addition. Like, it makes me so happy when I see that mistake not being made. Just to reiterate that point. So we have multiplication here. We can distribute this 1/2 is the TLDR here. We end up with x squared times y cubed times x to the 1/2 times y squared times 1/2, it's just going to be y, times z to the 1/2. All right, now what could we do? Yeah, we can combine the y's and combine the x's. I like that idea. When I multiply base to a power times base to a power, what do I do with the powers? We're just going to add those powers up. This is going to be x to the, you could do 2.5. I don't like mixed numbers. I'm going to write this as x to the 5/2, but you could also do like 2.5, whatever you want to do. But I'm going to write it as 5/2 times y to the, now y cubed times, what's the power on this y here? 1. So y cubed times y to the 1 is going to be y to the 4th. And then there's nothing going on with the z, so just z to the 1/2. And we are taking the log base 11 of this significantly less monstrous thing now. This is actually a lot more doable than one. So basically, the exact same problem that we looked at above, except now we have powers, but now we have a rule that lets us deal with those powers. So how could I split apart what we see here by my product rule?
Just 11x to the power of 5. I was thinking going to
Yeah, just keep on going here. And just to wrap things up, make everything look super nice and clean, how can I further expand this? What can I do with each of these powers? Bring them down to the front. So this is going to be equal to 5/2 log base 11 of x plus 4 log base 11 of y plus 1/2. Thank you. Log base 11 of z. Very good. The other approach that I would have considered, this is, I think, a perfectly valid approach. This works really, really well. The other thing that you could have done is separated this, like have this been m and this been n, and just separated like the part that is being taken the square root of and the part that isn't. I think that would also be a pretty good first step, is just like splitting it apart, just one of those pieces at a time. Thing that I want to note is if we did that, and we ended up with like log of x squared y cubed plus log of, we'll say xy squared z all to the 1/2. And we apply the power rule here. So we take this 1/2 and we drop it down. When we break apart this second logarithm, this 1/2 needs to hit all of it. All right. So just something to be really, really mindful of. In this case, this 1/2 is distributing, kind of distributing into what we have here. You want to be very, very careful with your parentheses as you break this apart. That is especially going to be true of the quotient rule. where that negative is going to distribute into your broken apart logarithm, the 1/2 distributes into your broken apart logarithm. Yeah.
After you break that down, you can combine the like.
And then you could combine the like terms and you should get exactly what we got here, where like this would become 2 log base 11 of x plus 1/2 log base 11 of x, which combines to be 5/2 log base 11 of x. Exactly. Yep, precisely. All right, questions with where we are? We'll take a look at the other pieces from example 2. We'll do that tomorrow. And then we're also going to finish up. We'll do example 3 tomorrow as well. And then the plan that I had with the rest of the day was quiz review. And so I would say come in with questions. Come in with questions, and we can spend a lot of time in class just working over were there any things from the classwork that were being particularly difficult that we would like to review. But in the meantime, we got about 10 minutes left. You guys are free to work on the classwork for the remaining 10 minutes here.